Good morning, everyone. My name is Olayinka. I'm at the School of Engineering and Informatics. I will be talking on rotation invariant graph neural networks or skeleton-based human activity recognition. Quite a mouthful, but hopefully we get into the details. I'm doing this work in collaboration with Dr. Phil, also at the School of Engineering. So this is the outline for the talk. We'll look at the problem, we look at the motivation for the model, we look at the model itself, and then we discuss the results. So to kickstart, has anyone here been to a football stadium to watch a football match? Oh yeah, we have a handful. So for that reason, some persons might decide to stay at the very top there with the fans so they could quickly get out just in case you are losing the match, which is okay. Some persons might be closer to the stand. Some persons even very close to the action. And some unlucky bloke might just be having a pillar in front of his view. And you probably would want that, if possible, you could be able to see every possible orientation of the football match as it's going on, being able to identify the offside when it happens, just in case you need to have a fight with the linesman against your team. But that is not possible except for us who are back at home watching from the TV from the comfort of our rooms, and we can see everything from all orientation. So why is this a problem? In so many other sports, also in other applications as well, you would see that when you consider, in this case, this is a baseball sports, and you try to extract the skeleton, you see that you get different poses from different camera views. What you want is a model, in this case, a graph neural network, where if you train on one skeleton orientation and you get some particular vector embedding, and you test the same action but the different skeleton orientation, you should get the same vector embedding. That is what you want. And to achieve that, you want your model to be rotationally invariant. And what do I mean by that? When it comes to training in deep learning models, the general approach is you take your data sample, you apply some transformation, whether it's for scale, whether it's for translation, or whether it's for rotation. And then you apply the model to that itself. But if you focus on rotation, the problem with rotation is that you have, aside the fact that there are 360 degrees you can go, and then there are different orientations where you have the XY orientation, you have the YZ orientation, and of course, you also have the XZ orientation. So many orientations you can go through. So you can't always transform or pre-process to capture all of that. So what you want instead is a model that composes rotation as part of its features, or in essence, a rotationally invariant model, where you just take your sample, you don't care what the orientation is, and you, whatever the task is, whether it's for classification or for regression, you get that out there. So this is the model we designed, where we have this module, which is still the usual graph convolutional network, but we added an additional module there that captures this rotation across different orientations and, of course, across so many angles, or all the angles, if you can think of it that way. And that's the temporal bit of the model. It's not interesting, so we move forward to that. So we're working with the NTU data set of 60 classes, where we train on one view of 0 degrees, which is just facing you, or 90 degrees from the side. And of course, we test on a different view of minus 45 or 45 degrees. And here's another example where the individual is saluting. So what about the results? We see here there really isn't anything interesting, where compared to the baseline, our model here, different strategies of our model actually matches the performance. And when we consider another case where we have the skeletons, it is trained on aligned skeletons, as we saw previously, and then it is tested on unaligned skeletons, where you have a different orientation for whatever reason, maybe the camera fell, but you get the idea. And you ask, okay, how does the model perform even when we train on one type of orientation and we test on a totally different orientation? And drum roll, please. We see that the baseline drops significantly to 18%, And our model, in a way, maintains a 15% accuracy, despite the totally different orientation. And this says a lot. It tells us that rotation invariance is somewhere around the corner for our model. Like, we're just there. We just need to probably make some changes to our strategy and add more invariant properties to our model. And possibly, maybe next time whenever I give this talk, I'll probably say that we maintain the same 91% accuracy. And one other thing we also observe is that a skip connection in our model does improve our accuracy very well, but also it deteriorates the invariance property, in this case, that we want. And we also observe that increasing the partition of the angle that we are training on also further improves our rotation invariance property. So this work is part of our intent maps a research project I do alongside Phil, and of course as part of my pathway fellowship here at Sussex. Thank you very much. Questions?
It's very interesting. Do you have any constraints on the distance between some of the sensors? For example, you have 2 for the feet. Would you consider a constraint to say this distance is going to stay more or less constant or within a 5% difference or something? Couldn't that make your model even more precise?
Okay, if I did get your question correctly, for the data set we work with, no sensors are attached to the individual. The data set uses a Microsoft Kinetics camera where the coordinates of the joints are estimated. So the individuals are free to do whatever they wish. And if we go to that case where we have to attach sensors to the individual, I think that would also make some changes with the results or what we expect to get. But for now, we are not considering that, being that those sensors.
Yeah, but I mean, even if you don't have sensors and you obtain this data differently, in the model, could you use constraints to get some of those distances set? And do you think it could make your model more precise? If you had a physiological information, you think adding that could add also precision to your model?
I would agree that would be the case, because the more additions we can add as biases to the model, and of course, in a way, that possibly also constrains the model to probably perform well on this data set because it has the special source about that data set, which is good. But one of the things we're also trying to do is to ensure that the model generalizes even beyond the data set. In this case, we are much more interested in the orientation of the data sets that was captured and tested upon. Yeah. Thank you.
Yeah, thanks. It's really, really a great talk, and I love the use of a prop as well. It's very nice. So I was wondering, would it not help to pre-process this into a canonical coordinate system? So you're starting off saying, "Oh, I've used it unaligned," but you could use the trunk of the body to align with one of the axes, and maybe as a simple piece of pre-processing. Would that not help remove some of the need for complete rotational invariance?
Okay. Yes. You're right. The catch here is, would we always need to pre-process the data? And even if we pre-process the data, do we expect that the data sets we find in the wild would conform to whatever pre-processing technique we adopt? So using the canonical angles and the other recommendations you've made, very possibly that would probably save us a lot of stress and just get our results and get the best accuracy. The emphasis here is we are saying in the absence of that, where we don't want to perform any transformation, we don't want to assume that we know, because the assumption here is that we know the properties of the data such that we can incorporate this form of pre-processing. But what if we don't have that information, where we just want a situation where we can believe that our model just needs to get the data and output the results, And that is where the invariance property becomes very useful, which is the same thing that applies to CNNs, where regardless of where the cat is on the image, because it's translation invariant, it always identifies the cat. So that's the point, yeah.
I had a question about the skip connections tend to have a detrimental effect on the invariance. Could you briefly, I guess, elaborate how?
So yes. So what we did observe was while training the model, when we increased the partition, probably I didn't give the details of the partition here, but when we increased the partition to 20 partitions, it improved our model significantly. But when we have just 6 partitions of the angles to work with, we could see here that the skip connection, which we used, did give us a 94% accuracy. But in terms of when we tested on the unaligned skeleton, it drops to 32. But in this other case where we don't have a skip connection, we still maintain 47. So there's a paper I probably would reference where they showed that what happens when you add a skip connection is it more or less changes the landscape of your loss function, where it is easier to reach your optimal. So what happens here in this case, your model is able to train fast enough, get to the optimal value. But what you lose is by losing the landscape, you lose properties where the model will probably follow a certain path during training, the path that maintains the invariance. But adding the skip connections just more or less gives you a shortcut to get to the optimal. But then you lose the invariance property you should get as part of that training process. Yeah.